All right, so we are live. And hi everyone, I'm excited to interview Soheil Eshkevari. He's currently postdoc researcher at MIT Sensible City Lab. He did his PhD at Leha University. He is interested in machine learning, structural engineering, and crowdsourcing technologies uh, are his passion. In this interview, you will get to know Sohail's journey, his thoughts on AI, deep learning, and its applications in structural engineering, and also we'll get to know a bit deeper in his research topic where he used reinforcement learning in structures. So, without much ado, we'll jump into the interview. So, Hill, thanks a lot for your time to do this.
Thank you very much, Mayor, for inviting. I'm happy to be here for this opportunity.
All right. So, Sohil, can you tell us about your background, where you grew up, and what made you excited to study civil engineering?
Sure. So actually, I'm originally from Iran, and I was born in the capital city in Tehran, and I was all my life studying there, living there. And so I would say the first time I got interested in science and engineering was like some maybe middle school or high school. I was lucky that I went to a very good school, and there were like inspiring people everywhere, both my like colleagues, students, and also the teachers we had. They were great. Totally out of box, like sorry, totally like thinking in out of box and like had different perspective to science and engineering, and that inspired me a lot. And later for college, when I had to choose major, so my father is an engineering, and I would say that actually he was pretty inspiring engineer, because it's not just me. In our family, we have more than, I would say, 10 civil engineers that all, I guess, are inspired by my dad. So that was my first preference, but I really liked computer engineering, computer programming, and also architectural engineering. So this was the list of my major that I like to go, and just happened to uh, I got accepted in civil engineering, and that's how I ended up doing it. But as it went further, I started my bachelor's, master's. I got more interested in that. But I would say that at some point, especially in my master's, I was working also in a company, and I got curious about integrating advanced technologies to the classical civil engineering, but that sort of was a very big missing part of the technology. And that actually basically motivated me to apply for PhD. And I again find myself lucky that I could work on Lehigh University with Dr. Shemin Paksad. He is expert in structural health monitoring, and this field is a very good place for combining multiple disciplines. And yeah, that was how actually I got interested in tech and programming and yeah, this stuff.
Oh, quite interesting. Even like my family, my father, mother, brother, all are civil engineers. So I feel that. And so you were quite interested in like technology right from the beginning. Like, when was the first time you got exposed to machine learning?
Yeah, for machine learning, actually, it was in my master's. Sorry, it was bachelor's actually. That I had an independent study with the concrete material professor, and actually we had this chance to start working with some like PhD researchers or postdoc researchers, or actually even like affiliate researchers on some concrete material projects. They were actually trying, basically, what was just no, when I think about it, was not very complicated research project. So they basically wanted to try different combinations of material for concrete mixture and see how would be the improvement. And for that, they were using genetic algorithm and like some probably Gaussian process to feed some functions so that they can maximize certain performance in concrete. And that was my first exposure, but I actually, it was very unfamiliar back then. I had no idea what's going on. But then it was a while of disconnection, because in my master's, I did classical civil engineering, like detailed design of steel structure. I really loved, I learned a lot about the whole process of research, conducting research in a formal way in my master program. But then again, I started learning about machine learning in my PhD. But I started with like online sources, which are great. But in addition to that, I had the chance to actually taking some advanced courses from other departments. And that made actually, I think, improve my skill set.
I see. And can you provide us like high level overview about like what are some research projects you did up to this date and some highlights?
Of course. So I would, it's pretty actually extensive if I want to talk about whatever I've done so far. But I would start from my just PhD part, which actually the main topic I'm working on is structural health monitoring, specifically on bridges. And the general big picture idea is that uh, we are actually thinking, or we are envisioning, that if we can use smartphones to collect data, vibration data from bridges, and process this data to get continuously get some updated information about bridge structural health, which actually seems like if that can happen in practice, this is a revolutionary advancement, because actually it's super scalable. You can immediately use this technology everywhere in the world. And we know how infrastructure is really expensive, how costly this could be if we just wait for them to uh, stop working and we rebuild them. It's going to be super costly. And if we can keep eye on them 24/7 always, then we can actually start repairing the bridge in more sensitive times so that we can avoid further costs. And that's the general idea. And for this goal, actually, we have multiple challenges toward that. For example, the state of art, I would say, in bridge structural health monitoring is to use sensors, like wireless sensors mostly, but in a fixed manner. So we put sensors in fixed locations, and they collect data for a while, send this acceleration data to a server, and the server process this data to get mode shapes, frequencies, like mostly modal properties. So I would call this modal system identification. And this modal information can be used for basically for model updating to begin with. And also, if you track these values in time and you see some sudden changes in these, it's basically a trend line uh, tracking. And if you see some changes, this could be an indicator of damage. And then you can go and spend more time, have a closer look. But so fixed sensor is the state of the art, but how to change it to mobile sensor? Because if you use sensors that are moving, then your data is not just a function of time, but also a function of space. And you don't have much control on the motion of these sensors, because we are envisioning that vehicles act like sensors for us, and you cannot control the driver's behavior. It may go slow, fast, stop. And so these are the challenges. One part of my projects try to address this problem, like how to deal with mobility of sensors, the variations, randomness that exist in this problem. Which is, I would say, the easier part. The more complicated part is that if you have, so again, in our ideal scenario, we are going to use smartphones for data collection, not advanced sensors. And smartphones are very low level sensors in terms of like motion measurements. The frequency, like sampling rate is not so high, resolution is not so high. We try to circumvent this, like address these challenges by aggregation. So instead of using one phone, you can look at a bunch of phones all together, and hopefully you can have a more informative data set. But still, there are some challenges within this data. For example, since you're using smartphones inside vehicles, and vehicles are driving, vehicles by themselves are dynamical systems that add up a lot of noise to this signal. And also there is road roughness, especially like generally roads are not having good conditions, and they add a lot of other types of noise. So basically you have a very complicated combination of signals that you collect with phone, and what you are interested in is pretty much the lightest, the smallest component to this combination, which makes it a very challenging problem. So we tried different approach for that, machine learning approach, signal processing approach. We actually had some success, but this part is still ongoing. Yeah, that would be the overarching or arching actually idea of my research. The main focus was of research, but other than that, I was always curious about using new technologies, different fields. Like this RL controller is an example of that, which actually I got the idea. I'm just one of the actually collaborators on this research, but the idea started when I was taking this reinforcement learning course at Lehigh, and I learned about the MDP, the Markov decision process, and how nice this framework can match to a lot of applications in civil engineering. And yeah, I was very curious about that, and we started working on it, and it ended up working nicely. And it actually is just the beginning of a path, and we think there is still a lot of ongoing, like future works on this that can be done with reinforcement learning. But that is a side project. I collaborated on that with my colleagues, Soheil, which is my sister, and Debarshi San, great collaborators, both of them. And they actually yeah, but basically this is mainly the project for my sister, but I collaborated with her, and I really liked that. Actually, it was amazing experience.
I see. Quite amazing. And like I was curious when you were suggesting sensors. So like how is the workflow? When I'm walking over the bridge, I send the data from my phone to the cloud, and like is there any gyro sensor which is taking care of it?
So yeah, that actually is a good question. So there are multiple components in the pipeline of this data processing. So the data is collected by the smartphone sensors, and then we have a phone app, multiple phone apps, but one is being used in MIT. It's called Good Vibrations app. And this app basically sends the data to a server, it stores the data in certain cloud, and we download that data. But that data is very messed up data. It doesn't have right orientations. It's noisy. It has also trend line shifts. So we do a lot of pre-processing on the signal. We remove the trend line. We apply multiple techniques to orient the signal. But we ended up actually using, so we also have gyroscope data from different directions. And so these parts is done all as pre-processing, but we just rotate the axis to very simply, just using gyroscope angles, rotate the signal to actually global axis, and use the maximum, which is vertical direction, as the input for or system identification. But still, other than these steps, which actually take care of the data quality, we still have some other filters for like resampling, downsampling sometimes, filtering, windowing, so that actually we can make it as nice and as trimmed as possible so that it works out best. But then we do the rest of the pipeline, the applying the methods, the algorithms in Python in different frameworks, but this part is offline.
Got it. So is it like way too simple to call it like it's a regression problem you're solving, where like you're collecting sensor points and measuring the deviation or vibrations through those sensor, and then in the future you're predicting like what's the health of the bridge, like?
No, it's kind of like a regression problem. The title is okay, it is acceptable, but it's not like signal prediction or like using regression on the signal itself. So what we do is that for generally system identification methods, you have a background model for the problem. So for example, you have a state space model of the bridge, which has some unknown parameters like stiffness matrix, mass matrix, or you can rotate the whole problem or transfer the whole problem to the modal coordinates and get mode shapes and modal frequencies and stuff like that. And then we want, using this data, we say actually, if there are certain parameters, let's say gamma, for mode shapes, omega for the frequencies and stuff like that, we should expect certain signal. And we have this signal, basically you solve in one of the methods in StrideX specifically, which was not my work, Tom Matarazzo's work. And if he uses maximum likelihood, basically we get a signal, we want to maximize the likelihood of seeing this observation given a certain model that we assume. So it's regression in that sense, but it's not regression on the signal itself. But the methods I worked on, they are basically model-based again, but they don't use maximum likelihood. It's like a simple machine learning objective function, like MSE, for example. I can explain a little bit on that if it's interesting.
Yeah, like I was getting an idea, like, okay, if you want to solve a problem using machine learning for structural health monitoring, like one way is using like some supervised learning algorithms. Like overall, like you had one deployment using reinforcement learning. So what are some ways to solve like those problems?
So yeah, that actually is a very interesting question. So I think there are multiple ways. This is my personal opinion. There are multiple ways to deal with a system identification problem using machine learning or data-driven methods. I think this title might be more appropriate. Data-driven methods. So if you use black box method like machine learning, assume certain neural networks and just try to get a lot of data, you will have many challenges. First of all, generally in engineering tasks, we don't have much data to start with. But on the other hand, the accuracy is very important to us because it's not like saying this image is cat or dog. It's not this is not the level of accuracy we are looking for. The level of accuracy is that whether or not this stiffness matrix that we are estimating is within the 2% margin of the exact value. So that is a very different level of accuracy we are looking for. So that's why I would not always start from black box methods. I would look at the physics of the problem. And I did a lot of research on physics-based or physics guided. I wouldn't say it's fully physics, but there are some ideas from the physics of the problem embedded in the machine learning formulation, but still the problem looks like machine learning because there is like a model, there is an overarching model, but the components are small neural networks. And the objective function is basically, again, it's a supervised learning. There are some labels. We want to minimize the difference between the predictions and the labels. And another thing is, if you impose certain types of physical rules to your neural network, then we saw that in one research that actually you can train models with way less than amount of data, which is great. And it matches very well with the actual condition in civil engineering problem. But for example, going back to the beginning of my research, for the MIMC method, that was my first paper, it's actually stands for model identification using matrix completion. This, I would see it as a machine learning problem, but it's fully model based. So I assume that there is a bridge response, that mobile sensors, maybe I can share my screen to show that, maybe it's easier. Is it possible?
Yep, go ahead. Yep.
Sure. So can you see that?
Yes.
Okay, so the idea of matrix completion is that, so let's say we have a bridge and we have certain vehicles that are collecting data. These are vehicles that are moving, right? And there is a huge matrix that it's unknown. I call it spatio-temporal bridge response matrix, but it's not known. We cannot collect all responses in all degrees of freedom of this bridge, but our vehicles just collect certain coordinates of this matrix, right? So these are the discretization in space, and these are discretization in time. And vehicles actually happen to be in different time, space locations and collect bridge response at that specific coordinate, right? So what you end up getting is the sparse representation of this matrix. And then we know from the physics of the problem that this matrix is huge. Physically, the dimensions are super high, but this matrix has to be low rank because bridges, like the bridge vibration is dominant by a few natural modes. And just by applying this simple physical fact, we could formulate it very easily and like complete this matrix and then use the rest of the problem. I don't want to spend time on that. Maybe it's boring, but I mean, mathematically speaking, just applying this fact that this matrix has to be low rank, we could find a very similar problem in math and optimization, which is called matrix completion, and impose it to your problem and solve it in a very better way in my eyes. Uh, that would be my general approach, not just going to off-the-shelf machine learning method, but looking at the physics of the problem, what we are solving, and try to find uh, the best match. For example, this formulation doesn't have any nonlinearity in terms of like activation functions, having like ReLU or sigmoid or anything like that. It is machine learning. It has a lot of matrix multiplication and minimizing a loss, but it doesn't have any nonlinear. This is the objective function, basically. You don't see anything nonlinear here. This is the only function we apply on the observation, and this is not a nonlinear function. It's just a binary matrix. But I don't know, maybe it was a little bit broad explanation. I hopefully actually could send the message.
No, it was quite insightful, and like I totally feel that, because like structural engineering, like if you have like even a small percentage of error, like you're risking people's lives with it. So it's we need to be sure about the accuracy of the model. And just like I'm taking a step back, so what are like some like the reasons why one should use machine learning in structural engineering? Because like I was reading papers from Autodesk, and there was one paper where for structural optimization and stiffness calculation, generally it's like take time intensive task, so they were using machine learning to reduce the simulation time. And like there might be some mod like one way, using mobile sensors data, maybe it's reduces the cost of those installations, so it's cheaper, and also you get a lot of data points. So what are some motivations, and like how can we use this in regular work?
So yeah, there are a lot of motivations for us to use black box methods like machine learning for exactly for like computationally extensive or generally slow processes. Like I think generally in engineering, whatever tasks that can be modulated, can be prototyped, these can be replaced with machine learning at some point. Like even in design, in structural design, it's a very broad field. It has a lot of like avenues that you should check, like multiple tens of checks just for designing a certain member. But these are repetitive. You're repeating this process everywhere. And if you have a big enough data set, you easily can replace it with way better, probably machine that can do this task. The same for other majors, like even medical sciences and everywhere. But again, for designing them and to be successful, I think we shouldn't look at the off-the-shelf method. It matters that we actually dig deep into this problem, try to find physical connections, and like use those physical connections as constraints, and then try to solve the rest of the network or rest of the problem with machine learning. But in terms of the motivations, I think design could be a huge part. Most importantly, I think structural health monitoring already has shown great potential for machine learning because you're dealing with data which is highly noisy, highly actually incomplete sometimes, and it's very helpful to actually we can have some black box methods that replace previously model-based methods. Uh, Other than that, I think, for example, like for generative design, these are not my expertise, but I've seen beautiful works that actually people use. I generally think that the parts of engineering that are, this is again my personal opinion, that are based on art and talent and creativity, these are the hardest tasks to be replaced by machines. So generative modeling is interesting, but I see this as a very complicated task because computers are not good in the like type 2 types of tasks, like those that we really need, uh, I mean, creativity. But yeah, repetitive processes will be all replaced, I would say, in very soon, actually, maybe within 10 years.
I see. And before we move on to the RL controller discussion, I wanted to know like what was the most challenging part in this research? Was it like data processing or feature extraction, or was it like getting into that accuracy level? Like,
So this actually is a good question. There are multiple parts that I remember as the hard, as very complicated parts. One is generally, so this problem as a researcher, the experiment is pretty complicated. So you cannot find easily a breach, and you cannot employ your app in multiple phones and simultaneously collect data for a while. And you end up using a lot of simulation, which actually slows down the process of upgrading this method to a practical solution. This part is challenging, but yeah, for example, in MIT, actually, we have this chance, this which is amazing. I would say maybe we are very few teams in the world that can do that, and that we have collaboration with some larger scale organizations that actually agreed to employ our app, and they are collecting data for us, and this process is ongoing, which is very interesting and exciting. But in Lehigh, actually, this was my major problem. And another problem is that, especially in machine learning part, if, for example, if you have seen my works on direct dynamical problems, like for example, estimating building response or dynamical response given it their input only, or going the opposite way in the inverse dynamical systems, finding the input of a dynamical system given its output. These are regression tasks in a signal level, as you mentioned briefly at the beginning. And regression on a signal, I found it as a complicated task. It's not easy to get high accuracy on that, and the architecture design is pretty tricky. For example, maybe autoencoder for us worked out better compared to other architectures that we tried, but and I can understand. For example, even very exciting things that are going on, for example, in computer vision, for example, faster CNN, these object detection networks. These are all, these do regression to some extent, but regression is pretty actually crude. It's not so accurate. So if you actually miss a pixel with plus minus 5 points or 5 pixels or even 10 pixels, you're still fine. You got the object. And again, there is major part of that, which is classification of that object inside that box. Again, most part of it is classification. But for regression, regression on a signal, especially if you're using recurrent neural network, you're predicting a value which actually has to be exact. Why? Because it's going to be the basis for the predictions of the future values. And if you start getting error here, then you start propagating this error everywhere. And so this was actually a very challenging problem for us. And I think we came up with some nice ideas to address that. For example, certain types of loss functions that look at a horizon instead of just one step ahead loss, or uh, we use like hard sampling so that we make sure that these hard samples are going to end up working pretty well, and don't start a deviation. And other than that, I think, yeah, these two came to my mind as the major complications that I faced in research.
I see. Yeah, that's quite insightful. Thanks for sharing. Now, I would like to discuss if you can walk us through like theory and implementation of RL controller, and like what was the approach. It would. Yeah, I'm curious to know that.
Of course, again, I can share and go over that paper, and maybe that's a better way. Uh, so, sorry. Yep, okay, here. So yeah, the RL controller, basically the idea is that, um, so again, I start with a little bit of history. When I took that class in reinforcement learning, I learned that, so there are certain types of problems, recurrent decision-making problems that can be modeled with Markov decision processes. And Markov decision process means they actually include certain types of problem in which at any time and at any decision making interval, you have a state which is a noisy observation of what's going on in the problem. It has to be also representative, actually, observation. You have this, you process this, you think about this, and then make a decision for this interval. And your decision is an action. The action will interact with the system, produce the next state. You have the next, and also a reward for this action. Then again, in the next step, you will have the same process going on repeatedly. So this actually MDP has a very long history. People started solving it with closed form solutions like dynamic programming and stuff like that. And reinforcement learning is a breakthrough that actually solves this problem, some versions of these problems in a data-driven manner. And I actually was started being curious about use cases in civil engineering, and I found structural active control as one of the, actually our team altogether found that this field is a good match and very similar to the reinforcement learning framework. How is that? We say that in active control, we have basically this loop going on, which is, so we have a structure that is, a ground motion is applied to it. Let's say this is applicable on just buildings standing against earthquake. And this is the earthquake applied to the building. The building responds to that ground motion, produce a dynamical response, and the state actually gets created. And this state is the, let's say, the classical definition of state in the state space equations of a dynamical system. Simply put, it's displacement and velocities and at all degrees of freedom of the building. And then we have sensors, but our sensors, this is one start point that actually our method deviates from classical, maybe RL setups. Our sensor cannot get a full representation of state. It gets just a substate of subspace of this full state. And what is that? It's basically acceleration, which is not displacement and velocity, and it's not necessarily complete. So we can have acceleration, let's say in a 9-story building, we can have acceleration just in 5 stories because that's how it is. We have sensors in just 5 stories, which is going to actually have a detrimental effect on the performance, but that can be captured within this framework. And also sensors calculate reward. And here the reward basically, it's somehow counterintuitive with respect to the word. It's not reward, basically it's the negative of punishment. Basically, what we measure is the drift, inter-story drifts, accelerations, and stuff like that, and sum them up and multiply a -1 to it so that it acts as a reward. So as it gets closer to 1, we are happier. As it becomes smaller or less negative, more negative, these are bad. We want to avoid it. And these are the inputs to the RL controller. So this part basically is a neural network, not a very deep neural network though, but it's still a neural network, and it takes an action. The action can be the applied force or applied, I would say, effort in whatever mechanism we design. For this problem, we assume that there are actuators in different stories and they apply forces, and this action is the actual actions that those actuators can take. And they apply these actions to the building, and the building continues this process so that it can, this neural network can control the motion, minimize the demand on the building. This is the general setup or the scheme of the problem. And very important actually finding, or like not finding, but I mean output of this work is that we introduced a Python class that is compatible with, it's a standardized environment that can be used with a variety of optimizers. Because for those who are familiar with reinforcement learning literature, the most active part of this actually uh, domain is that people try to find better optimizers. It's tricky part. It's a tricky problem. Our reinforcement learnings are not, some of them, most of them are not sample efficient. You need a lot of training so that you can find an optimal plan. And your optimal strategy may not even be the global optimum. Maybe just end up finding a local optimum, which sometimes is fine. Even in this setup, we don't know for sure that what we are finding is global optimum, but actually we just know it outperforms existing active controllers. But this class actually has a lot of functionalities. You can just explore it. You can modify the mechanism that we introduced, which is actuators, with your desired controller. I don't know, whatever you want to apply, like tendons or whatever, even base isolations. You can change the loading type from ground motion to wind load or whatever types of loading you want. You can change actually even the building type. It can be bridge. These are all possible. So this framework is pretty flexible, and I hope that people start like cloning this. It will be up in GitHub sometime soon. We are trying to make it as nice as possible, but I think it gives a lot of opportunity to just explore this active control problem with different setups, and even actually make it more complete as what it is. Yeah, this part actually probably took the major effort to make it a nice standardized gym environment. So I think you're familiar with gym, which is the classic, I think it's OpenAI package. And yeah, you can easily try different state-of-the-art optimizers like PPO, TRPO, DQN. So it depends. Like, for example, in this setup, our action space is continuous so that the actuators can apply whatever force they can within the certain range, of course. So by actually setting this assumption that your action space is continuous, you automatically lose some optimizers to try. You cannot use Q-learning anymore, for example. But this is not a problem of RL controller. It's a problem of your definition. But you still can very easily change it's just one line of code so that you can try a totally new algorithm and run it. I like this part a lot. And so later on, a very important point actually here I have to make maybe in this plot is that compared to, so whenever actually you have questions, just stop me, sorry, I just want to explain whatever I remember. Um, a very important point in this special active control mechanism that we are proposing here is that compared to the existing active control strategies or works, or method does not need to know the system mechanics of the building in advance. So this is, again, a general problem in reinforcement learning. There are multiple ways to solve reinforcement learning problems, one of which is that you start by learning the model first, and then given the model is known, you try to find a strategy, find the optimal policy. But the most actually advanced way of the most recent optimization methods in reinforcement learning research field is policy gradient methods or actor critic methods. These basically just aim for finding the policy directly without knowing the model. So the model learning part is integrated within the training process, which is actually a very important part in our setup in the civil engineer, in this structural control problem, because finding the definition of the model, the mass matrices, stiffness matrix, this part is a totally separate task. It's very costly. It has to be done by system identification, model updating. But this framework, our control doesn't need that. Actually, it just starts interacting with the system, and it implicitly learns the system and exploit that knowledge. And that is a very big, I think, finding. We hope that we could emphasize on that in the text, but actually it was good that I could explain it here.
I have a question. So,
Sure.
uh, just to get it right, like, so the RL controller is trained. So, is it like once the building is constructed and pre-occupation, there is some calibration for the RL controller based on the sensor data. And when there is like a earthquake or heavy wind, like the controller is suggesting like how to actuate the building. Is that the problem?
Yes, it actually basically plans the actuators how to apply force in different degrees of freedom so that they can minimize the overall demand on the building, minimize the building shakes, for example, like all other controller systems. That's the
Got
objective. Yeah. So actually at the end, to show how well the method works in terms of performance compared to the counterparts, we worked on a benchmark building, a 5-story building. And like this result, for example, is just summarized result of what our controller is doing. So the uncontrolled building response in the 4th story is shown with this dotted line, and the control with 2 methods, reinforcement learning and another controller modeled with LQG, which is a known, highly like valued or respected active control strategy. We designed the controller with LQG and compared it with RL. Again, I want to note that LQG uses the system knowledge. For designing LQG, we assume that building is known, but RL didn't have this advantage. So the responses are compared here, and you can see that, so in terms of controlling drift, they do both do almost the same level of performance, actually can perform similarly. But yeah, here actually maybe RL works a little bit more smoothly. And also in terms of acceleration or base shear, like total demand in base shear is also a measure of performance. We see that sometimes it actually matches with the uncontrolled. It's not way better, but after like damping out or canceling out the peak of the quake, then the controlled mechanism worked better compared to uncontrolled system, which both actually are satisfying. So another flexibility that we have in RL controller is that you can design the objective function however you want, so that you can minimize your parameter of interest. Here, our objective function mostly weighed on the inter-story drift, and that's why inter-story drift is controlled pretty well. We had also components in the reward function, in the loss function for the base shear, but the coefficient of that term was way smaller than inter-story drift because we were focused on inter-story drift, but you can easily change it. It's just a number in the class that you can change. So this was just a very small example on one earthquake on 1 degree of freedom. We summarized all the results here in terms of some performance indices like J1 to J4, and the descriptions of J's are shown here. For example, J1 is the maximum controlled drift over the maximum uncontrolled drift. On all the earthquakes, actually, we measured that. J2 is the maximum of acceleration on the controlled over uncontrolled. And J3 is the energy, signal energy, I think, in the the controlled system compared to the base energy of the base shear in the uncontrolled system. And J4 is not the energy, it's the actual value of base shear divided. So basically these measures, I don't want to confuse, not you, even myself, with these parameters, but these are basically general performance measures that people use in control literature to compare systems. And we see that we are comparing RL and LQG in these plots over a variety of earthquakes, not just one earthquake. And the red one is for LQG, for RL, and these are story levels. And you see that almost everywhere, RL does a better job compared to LQG, which already knows the model. Again, I'm emphasizing on that, which was pretty promising. This is actually, I would say, a summary of this paper. I have some other additional information to share, but
I see. So like I haven't dealt with the sensor controller, so I'm just curious. So once the sensor is installed, like is this like gonna be like a edge device or like a chip where you you do, or does it need like cloud information to simulate the next action? Like, is it
Yeah.
just
What happens is that you train the network hopefully before the event. So you have the predictor, you have the agent ready when the earthquake happens in an ideal scenario. And the earthquake actually the where this agent is stored, it's somewhere inside the building. I think it's the safest. Maybe even cloud is not the safest because maybe we lose communication within an earthquake time frame. And it's inside, it's an intranet connection that actually just sends a request, a query to the computer, what would be the next action, and the action comes back and the actuators apply them. That's how it's going to be applied. There are a lot of challenges and questions in terms of practicality. So this paper mostly focused on the just the idea development or just proof of concept that this RL controller approach might be even better than advanced model-based controllers. But in terms of practicality, there are a lot of remaining works that we are already working on that. For example, what if the connection is lost for a few seconds or three microseconds or whatever level? Can RL controller catch up and still control the building? And this is not a result we present here, but our preliminary results showed that yes, it still can catch up. Not, of course, not with the same level as control, but it still can improve the performance. Another thing is general. These are general challenges, the general actually suspicions people have about active control systems in general, not about reinforcement learning though. For example, what happens if the observation is very noisy? Because if the input is bad, the output is going to be bad as well. And so we are trying to model different levels of noise and see what's going on with that. And these are still ongoing. I mean, we are aware of the practical challenges and we are trying to improve.
I see. And lastly, like, what is the reason like RL controller is performing better than like classical rule based approach? Because like I think like even they foresee for each action what's the response of the building and then predict the next action. Like, what gave the model more a better accurate behavior?
This is actually a very, very smart question. I agree with you that it sounds a little bit counterintuitive that why should a model beat a model based? So there are two reasons that I can come up with at the moment. One is that, first of all, uh, for LQG, what we do is that we assume it basically has very similar structure. We have to define a loss function and work on that loss. But the loss function is a static measure. It cannot change in time during the training process. Yeah, this part is done by Devarshi Sen, and he did a great job on terms of like finding nice responses and everything. I have to mention that. But the part that for RL controller, what we did actually is that we have a thresholding so that if part of the like our loss function includes multiple components, one for the inter-story drift, one for acceleration, one for base shear and stuff like that. If one of these components actually exceed the threshold, we penalize more. So this doesn't exist in a classical definition. We couldn't, because if we add that to the algorithm of LQG, there is no guarantee for convergence. LQG has its own structure. It works based on a static loss function. This is, in my knowledge, maybe some advanced research actually has shown that you can change that as well. The second thing is, generally, this is a very interesting finding in reinforcement learning methods that are policy gradient methods, like actor critic methods. They don't put too much attention on the actual mechanism inside the system, and they just focus all the attention to find a mechanism to a strategy or a cheat sheet so that they can minimize the response. That's it, without any respect for the model. And that can be sometimes very useful. For example, let's say you have a complicated model which is high dimensional and it's very hard to explore. And if you want to learn it in advance, or even if you know this big like set of information, this is just a lose of space and loss of energy and effort, computational effort to store this and keep track of this model all the time, because the majority of this environment is useless for your decision-making process. But reinforcement learning just picks up the information, like the policy gradient method, just picks up the part of the information which is necessary and useful for the decision-making process. This basically, when you integrate these two parts, exploration and exploitation together, then apparently models actually do better job in terms of just learning efficient information for doing better, uh, performing better. That these two are my answers.
I see. Yeah, like I recall, like even DeepMind deployed like models, and they were training the models to learn instead of like focusing on one single particular game. So it's the learning strategy uh, which makes it quite interesting. So and I just curious, like because like there was that move 37 in AlphaGo. So I want to know, like, is there any findings through this reinforcement learning method that was like counterintuitive to way we think about it, or like something which is quite outlier thing in terms of strategy?
So in terms of the strategy that the system finds, or in terms of what we learned by using reinforcement learning, uh, I can say, for example, the second one, which sounds interesting to myself, I can start with that. Uh, we found that reinforcement learning, maybe it's because we are not knowledgeable enough, it's a very, very complicated way of learning, because of lack of back propagation and differentiation for each hyperparameter into the system. So it's a reinforcement learning is a branch in the family of black box optimization methods, and whatever you can do is just throw in an input and see the observation. There is nothing coming out of this box, and this makes it super hard to learn compared to machine learning. But in machine learning, when you calculate the loss function, then you can do backpropagate, and you can see what would be the effect of every single component in your network to this output, which is huge knowledge. But this is fully missing in reinforcement learning, and that makes it very complicated. So in my current research with MIT, I'm working on a reinforcement learning problem with traffic networks, and so far I'm spending 2-3 months, but the progress was pretty minimal, because just exploring that environment takes forever, and I cannot simulate this environment in a faster way, because anytime you want to interact with the system, you have to infer that simulator, and if simulator is not fast enough, it's going to take forever. So generally, when you try to think about reinforcement learning, make sure that your problem is tractable, can be small enough. And also another very interesting finding for myself is that make sure that you made your action space and your state space as small as possible. So don't think of reinforcement learning in terms of the actual appearance of the problem. For example, if you're dealing with a decision-making process that has hundreds of variables as action, make sure that I will assure you that you cannot use all these actions together and find a way with reinforcement learning. It's impossible. Make it as small as possible, like a handful of actions, and then think of some smart ways so that by having this handful of action, you can go back to this wide action set and continue this process. These are what I learned basically from the reinforcement learning part. In terms of what we learned from the strategy that reinforcement learning found in RL controller, it's an interesting question, but we didn't dig into that yet, like comparing what this strategy is doing compared to what we expect. What we found is, so yeah, there was one finding, was that another interesting feature in this RL controller is that it learns from the exogenous input that is just random. It's just random Gaussian noise, which is interesting, because if it depended on actual earthquakes, then this question can arise that we don't have these earthquakes applied to that building. How can we get that? But we don't rely on actual earthquakes. We use noise, white noise for training process. And it ended up, actually, we found out that it works well with earthquakes. This is interesting. But we found that compared, if we assume that this Gaussian noise is the benchmark, we found that if you superimpose some random impulses to this ground motion, to this white noise, just randomly locate an impulse somewhere in that as the input to this network, the network learns very well to counteract earthquake pulses at the moment so that it improves the performance substantially. That was another thing that we found. Still, the white noise only worked well, but white noise plus impulse worked even better.
Got it. And if I were to deploy this RL controller for my next project, like what's the procedure? Should I just like clone the report, train it for my building, like install it the sensor, train it for my building, and is good for deployment? Like I just want to know like application if one has to adopt this.
Yeah, so for this level, of course, this is you. I want to make sure that you're not going to use it in your building because it's not ready for that. But for research purpose, yeah, what you have to do is just clone it and introduce or set the mechanical properties of your building, basically mass matrix, stiffness matrix, damping matrix, and the properties, the location of the actuators and sensors that you have. These are all easy variables that you can set, vectors or arrays, stuff like that. And yeah, run it. You have to train it for a while. This actually, the whole package for optimization, you have a variety of packages to use, but what we used for optimization was stable baselines package, which is a nice package for learning. It has a lot of advanced optimization methods embedded, so you can easily exploit them. Yeah, and run it for a while, and you just track in TensorBoard. You can track the reward function whenever. So another thing generally about RL is that there is no exact solution. There is no global. You cannot simply know if you get to the global optimum or the best performance ever. You just have to be satisfied with the result and stop it. Because yeah, maybe if you run it for a very longer time, it can still improve. But generally, like RLs are sometimes very unstable, so you may want to stop the training process early, and the performance is still satisfying. So yeah, that is what you need to do. It should be pretty simple.
Got it. And honestly, I'm loving this discussion and I wish it goes on and on, but we have approached the 1 hour mark. So I want to dive a, a bit into like your upcoming projects and advice for people who are getting started. So uh, uh, a question I had is, according to you, what are some roadblocks faced by AEC industry to adopt this kind of models or deep learning techniques in their workflow?
I think we already within the discussion mentioned some of these issues, maybe a little bit repetitive. One is again lack of data, but I think the lack of data will be addressed very soon. Maybe already is changing. This situation is changing very fast because of the abundance of sensors. Uh, Another thing is that we have to integrate models. We have to integrate the physics of the system so that we can reach the accuracy that is acceptable to the experienced engineers. So, actually there is like two groups of people working in AEC. People are like young engineers, just graduated. They're interested about integrating technology, and experienced ones that are not easily, they don't easily accept whatever you say. To make them accept, you need to have a very good accuracy measure. You have to show that the performance is really it's really inspiring. So to do that, I think one solution I found is to integrate model, because you can explain this. It increases the interpretability, And also it actually has a lot of effect in increasing the accuracy that you want. Data efficiency, we already mentioned, it's not matter of adding more data, but you can use techniques, adding some constraint to your optimization process so that you can you work with smaller data. Uh, and for very broad audience of young researchers, like I mean undergrad researchers maybe who actually want to start working on machine learning, I review papers, I see papers that people in civil engineering or AEC used machine learning that I would say they are just basically incorrect approach for to take. Like when you don't have enough data and you are working on high dimensional data, just working with with machine learning because it's the most like hot topic, it it was once very interesting approach and people gave you good feedback, but it's not anymore. You have to actually have something to say. Your method has to be superior, really, not just using a machine learning is not sufficient. Yeah, I would say, and I think generally it maybe I'm, of course I'm biased because I'm inside this industry, but I think the better years for like integration of AI and civil engineering is yet to come. Actually, in future, it's going to be even way broader.
I see. So is it like if I have an idea to propose in an organization, I should work on a weekend, make a proof of concept, and show it to the senior that okay, it's accurate, and I'm not just proposing something out of the box.
Yeah, because at the end you have to sell to those people. They have the clients. They know how to help you with the marketing. And if it just makes you happy and myself, both researchers, it's not gonna actually have actual effect.
I
That's
see.
my idea.
Totally makes sense. And according to you, what are some emerging trends in the field of AI or deep learning algorithms which a structural engineer should keep an eye on?
That is also somehow related to our previous conversations. Like I think generally interpretability is a big trend. Uh, and one other field that I'm curious about is multimodal AI, which means like you get data from different resources. So uh, you basically are not limited. If you want to know a bridge, structural health of a bridge, you shouldn't be limited to just signals or just drone videos, but an aggregation of all these data sources, which seems very promising. But I think some of them are not really practical in the university level because of the infrastructure they need. But the trend is coming. Actually, the trend is definitely there. And another one is that yeah, like semi-supervised or like self-supervised machine learning is also very interesting topic. Simply put, I'm also a student in that manner. I'm learning, but I'm just repeating what I learned. Is that for self-supervised learning, the idea is that when if AI or neural networks are trying to mimic how human learns, uh, neural network is doing very bad job compared to human. Why is that? Because when a baby is going to learn a new task, he or she doesn't start from scratch. They have a very good background of what type of problem is that, which category is that, and then just fine tune itself or themselves. So this is very interesting. So when we model a system, model a neural network and start learning it, we basically start from scratch. The weights are all randomized. And this is bad because we had very similar tasks we trained and we could start off those, like transfer learning idea. But self-supervised learning actually methods, I saw a paper recently, I think by Lacan, I think the French famous researcher in Google, I think, that they provided actually made a huge model for self-supervised learning that basically it has a huge data set of image and it tries to cluster images, maximize distances, basically just practice with itself so that it can have a very good feature space for whatever task you will have in future. And then depending on your task, you just put your labels at the end and just train it for a few epochs and you're done. Which sounds amazing to me. It's more realistic and closer to what humans basically do for learning.
Yeah, like that's quite interesting because I was reading about multimodal like through Dali, and also like there's some attention gain, like even like transformer, like it's getting more accept wider application from like language to images and graph neural network. So I haven't yet seen like those models uh deployed in like structural engineering research, but I'm excited like how people take that.
Of course, yeah. Actually, transformers are also something inspiring me a lot. I tried to use it to some applications, was not successful, but the idea looks very interesting. The reason I like it is that in one of my very early research, I had similar idea. Of course, I'm not a computer scientist and I couldn't make it happen, but I was thinking, yeah, what if we have a simple, fully connected layer in which these layers themselves are not constant, they are actually functions, which is basically very simple explanation of transformer and looks very interesting to me. But yeah, of course, I see a lot of potential in that. I couldn't do anything with that yet.
I see. And what will be your advice to students or young professionals who wants to do similar work?
Um, I would say it's best thing I learned from my career path so far was that it's always better to be good at the fundamentals and the very deep understandings, and then try to build up on top of that. And for example, whatever we do, I come from a culture in Iran in which like engineering is a fancy major, medical science is a fancy major as well, but engineering is really very advanced major. But when I moved to the US, I learned that actually science is very very important. We didn't think about it that way back in Iran, and I think no, I know that if you have a very good understanding of math, then you may come up with amazing ideas that can be revolutionary, and you can use it in engineering or whatever field, and that will have way broader impact compared to what we can do as engineers. So it's always good to make sure that you are brilliant in math, you are great in physics, you know what's going on inside the problem you are interested in, and then use these tools in like next to the knowledge you got from the fundamentals, and this integration would be amazing. That would be my suggestion.
I see. And any like particular courses, books, or conference you recommend to people that might accelerate their growth?
So this actually books are a lot, but the books, one that just came to my mind is relevant to RL controller. I think it's the obvious book is the Seton and Bartok book for reinforcement learning, which is amazing. And the interesting thing about that book is that it's a very understandable uh, book. Actually, you can easily read it. You don't need to have huge background in math. And just read it from the beginning to the end because it's amazing. It actually talks about different types of reinforcement learning problems that you can define, or black box problems in general. That book is amazing. In terms of conferences, depends again on your interest. For mechanical, like intersection of mechanical, civil engineering, um, I learned a lot when I attended. I had a few experience, but IMAC conference was really good, and also like IWSHM is also a very good conference. I like IMAC even better. Uh, and that's it. These are not very knowledgeable suggestions because my experience is limited on that.
No, no, it's quite like I think like during the hackathon you suggested this book, and I started reading that book, and it was quite insightful. So uh, I- and is there anything like I'll open the forum for like questions from the attendees. And before that, I wanted to ask like if there is anything we didn't cover in this interview and you wanted to share your thoughts about, or any technical or non-technical information.
I don't think anything that was specifically in my mind I didn't say. Yeah.
Awesome. So now like if the attendees have any questions, like feel free to jump in. I'll also see if there are any questions from the live stream. S- So Aditya Sharma had a question. I think it was earlier during when we were talking. So he's asking, so we are trying to apply forces through actuator to reduce the effect of earthquake while the earthquake happens. How will it be done for a new earthquake as the time history is not known?
Yeah, that actually is interesting, and I think we briefly addressed that. So what we learned, that's actually one of the achievements of the method. You can learn merely on the random noise or whatever type. You can actually come up with smarter way to generate some artificial inputs, and you just learn on top of that. But we checked it with unknown earthquakes to our network, and it still worked well. So yeah, the whole idea is that this is learned offline, and it works for the earthquakes that happen in future are unknown. How it's done actually is that, if you think about it, even in future earthquakes, I know that the ground motion is not known, but the states are known. Like whatever happens to the building, if they are within the similarity of the states that the network saw previously, still has an idea how to take an action that maximizes the value in this step. That's how this is done. It's not magic. I mean, it's similar to the actions it saw before.
I see. All right. So, and lastly, like, I wanted to know, like, is there anything from your whole career path you wish you would have done differently?
Yeah, so that the first one was I know myself as I have good fundamental knowledge, but even better, I would wish actually I was better even in math. I had like more advanced understanding of math and physics. Uh, and other than that, also programming for civil engineers, I think we start learning about that a little bit late, especially if you're just researching on that. You start working with MATLAB or Python. But I'm not saying programming just for the sake of being able to use these APIs or machine learning. I think programming also gives you a mindset of algorithmic thinking, which is very, very important. Uh, Also in a personal level, I as actually years go by, I would love probability and statistics more. Even in machine learning, actually whatever we do is just Bayesian inference, making our knowledge better based on previous experiences. And I think it's not just for AEC, it's for all humans. I think we don't know much about probability. We have to keep pushing that forward. This is also something I personally try to do if I have some spare time. These are just very general advices. Maybe people know way better than me that this stuff.
God. Yeah, so we have comments from Ritvik that it was quite insightful. It opened doors to learn more about the field of RL and construction, and thanking you for the advice.
Yeah.
So I wanted to make a last announcement. So in our next session, we'll be reviewing 4 lectures from this amazing course at ETH Zurich about computer vision applications in machine learning. So they have the slides uploaded here, and like Rutvig is also in the session, and we are collaborating to review few of their work and like how we can use those computer vision techniques in our uh, day-to-day work. So uh, I want to thank Sohil a lot, like for your time to explain all of your work. It's quite amazing research work, and I feel quite inspired, like from learning more and more about your work. So thanks a lot for sharing your thoughts.
Yeah. Thank you very much, Mayor, for providing this opportunity. It was great. Thanks.
Awesome. All right. Have a nice day.